This is Jim Hendershot again, and this is the second lecture regarding cooling of machines. This involves strategies, some strategies, and this is lecture number 34. Here's a cross-section of a simple induction motor with an external fan. You have this is typical of many machines, and the way this is cooled, this is a totally enclosed motor here with a frame around it, and the stator's in there. Rotor's mounted on the shaft, there's bearings in here, and maybe seals, maybe not. But this die-cast rotor has, they call it vanes on this item, but it's basically fan blades that have been die-cast on a rotor. We've seen that before. And when this rotor spins, why, it's a centrifugal fan that blows air around here and cools the end turns, and that air heats up pretty fast, but due to its motion, it flows on the inside of the stator, or the end bell there, and of course convection on the outside takes the heat away as that heat is conducted through the thickness. Now on the outside, to aid in all that, there's a shaft mounted fan like the ones I showed in the picture in the last tutorial. And so when the motor spins this centrifugal fan, the air is sucked in here because these rotating blades, see, the air has mass. So it doesn't seem like it does, but it does. And so that air is thrown out. When this spins, that air is thrown out to the OD. And so a pressure drop exists here. There's actually a vacuum created inside here because that air has been thrown out, and that gives you a pressure that sucks air in. So the only place for it to go is out. So it goes over the OD of the rotor, and some rotors the OD is smooth, some have fins there. Sometimes this goes all the way down the end, so it takes heat out as it goes over. So that's gives you the idea of cooling. Now here's a very large stator, a huge stator that's not near as compact as that one. As you can see, the laminations of the stator are stacked in packets with vent plates between it. We saw those on the last slide, or on the last workshop. And so what you have are the conductors for the phase windings go down these open slots, and they're in this chamber here, and they pass through these vent places, so there's direct contact. If you can get air or gas to go through those ventilation places, then you're getting direct cooling right on the conductors that pass through there. And to aid in that, even the outside is made up of a welded structure with all sorts of vents in it. So there'll be some kind of a suction blower system that will suck air off of these chamber out through all these passages, which will cause it to go from the inlets around the idea of the rotor through its passages, its vent passages across the air gap and out these passages, because the rotor needs the same kind of heating. It has conductors going down the slots as well. And these are those core vent plates that go between these laminated sections. There's ones for the rotor, this one's for the rotor, and these other ones are for the stator. This is a review of the same thermal conductivity. But so let's summarize the cooling options for induction motors, and PM and reluctant synchronous motors are the same. We have three methods. We can use air, or we can use 50-50 ethylene glycol and water, or we can use oil cooling. Now, how do you apply that? How do you use that as a heat transfer agent? Well, I just showed you an internal and external forced air cooling. I just showed you an example of that. In the other lecture, I showed you some pictures of some large motors that have external blowers on them that blow air through them. That's very effective. And at the end of this slide, I'll show you a unique low-cost cooling passages around a traction motor used in a car. Now, all these same methods are doable with either a PM machine or induction machine. But in the case of water ethylene glycol cooling, usually you don't spray this right on the rotor or the stator. That's not normally done. It's usually retained in a cooling jacket, a spiral cooling jacket. Sometimes there's holes in the big yoke of a stator that you pump this down those holes in the stator. They even put copper tubing down in the holes, stamped holes in the core of the stator, go from one end of the core link to the other, like flue pipes in a steam locomotive, kind of like that. And so the heat is extracted by the flow of ethylene glycol water, either around the outside or right through the yoke of the core. Some other, I'll show you a picture of a very clever liquid-cooled motor for the auto industry where they run the radiator cooling fan or radiator cooling liquid through it. The other way to cool, and this works really well for induction motors as well as brushes, is to use oil. In many applications you already have oil, like aerospace applications have oil, machine tool spindles have oil, and and automotive traction applications all have oil. For example, a good cooling oil is hydraulic fluid in a not hydraulic fluid, the automatic transmission fluid. It's a thin oil and it's a very good cooling agent. It's already available there, and sometimes they even have radiator heat exchangers to keep that cool. That's not uncommon. So the beauty of that is you're not adding a cooling system to the motor drive system. It's already there anyway because there's a combustion engine present. So and the way you can use that oil is in this cooling jacket around the outside that looks like the same one the water jacket uses, but you can also spray it directly onto the end turns of the stator winding if they're properly insulated, and onto the ends of an induction rotor. You can spray it directly on there, and you can even have the oil come around enter the machine around the shaft somehow, or be sprayed through nozzles in the end bells that with kind of a funnel shaped deflector to cause that oil to go in some passageways on the inside of the rotor. And I showed you some laminations like that for PM machines. And then the centrifugal force of the rotating rotor carries that around the outside at each end of the rotor length, and that is then flung or sprayed onto the end turns of the stator. That's a very effective, a method like that is used in the Ramey motor, the Ramey design motor that General Motors uses in the Volt. Here's this, here's an example of a inlet and an outlet for a liquid cool machine. Here's a picture I showed you on the other lecture, same thing. Two inlets, one inlet there, one inlet here, and these two are outlets. And here's a machine, a traction motor that's got a liquid cooling jacket built in it, and here's you've got your lead wires, but you also got your cooling hoses to cool the motor. Now this is this comes from Germany, from a company called ATE, and there's lots of these made. They're machine tool motors. This is an induction stator mounted inside of a water cooling jacket. It has these spiral grooves on the outside. This is the type of thing that's in there. This is what's inside that thing. And these are very popular and for drastic liquid cooling that greatly increases your density. Here's another example of a smaller motor. This is an aluminum, this happens to be a very high speed machine as well. I think it's 70,000 RPM. It's a permanent magnet machine, and you see the spiral groove in there, which is easily machined in on a CNC milling machine. And the stator is inside there, and it's been potted, it's been encapsulated inside this aluminum cooling jacket with a thermally conductive epoxy to also have a better thermal path for the heat in the end turns, so not just to be trapped out there in the air. And this, of course, has O-ring seal at each end, and this slips in another tube where the liquid ethylene glycol enters. Sometimes those are, like on machine tool spindles, ethylene glycol is refrigerated. They keep it at 70 degrees Fahrenheit. If they make it any colder, they could increase the power density and extract a lot of heat. But the problem, if they make it colder, then the cold is going to take condensate out of the humidity of the air, and it's going to cause rust to the machine tool and things like that. So they try to keep the cooling media at room temperature. Now here's some examples of fans and serious cooling fans. This is a motor and a centrifugal blower or suction device. These are the type of fan blades that go on the end of a shaft. These aren't inside the frame; they're on the outside. That would be in an enclosure like that would blow the air down over the fins. Here's another example. This got fins. That's got a can over there. Same with this one. One of these fan blades is mounted on the end of the motor in the back. That greatly improves the thermal capacity of these machines. These are NEMA IEC or IEC motors. Here's the class of NEMA motor enclosures. You could study these and see how they all work. These are not random inventions. These are planned and detailed. So if you're doing a new machine for an application, you get a lot of ideas on what kind of a frame you want to design for your machine. Here's some examples of some castings and extrusions used for housings, and this is one that I'm not sure what the advantage of this is, but we'll see in a minute here through some work that was done by Erland Persons Electrocraft that the fact that the fins go axial or radial is very significant, and we have to explain that. You might intuitively see what it is. This would work best if the motor was mounted vertical, as would this one. But if you turned this motor horizontal, it wouldn't be very effective because you'd have some trapped air pockets. It wouldn't have very good convection velocities. Whereas if you're going to have a motor mounted horizontally, it's better to have the fins concentric like this, because you'll get natural convection flow through the temperature of the surface versus the temperature of the air going by it. So, but we'll show you some tests that were done on that. The surface has something to do with it, whether the surface is finned or whether it's smooth. If it's finned, you're greatly increasing the surface area that's in contact with the air. That's obvious, and you can double or triple with fin design. You double, triple, quadruple the surface area just by putting fins on it. If the motor's mounted horizontal, natural convection is like this, or if the motor's mounted vertical, it's like this. Whereas if you have forced air, it doesn't matter how you mount it, because the air velocity is going to be blown from the shaft end across the thing. Now Erland Persson, who was a retired and deceased technical father of Electrocraft, one of my mentors in my career, he did a lot of tests before they designed their Brutic line, they called it. It was a brute of a brushless motor line, and he came up with these coefficients, and this is all based on tests of samples. Here's the degree C per watt characteristics of a frame that was 6 inches in diameter and no heat sink, and so he compared the degree C per watt values. So the actual values aren't meaningful to you, but the percentage difference between them should be applicable to any motor. And so here's his 6-inch diameter. No, I guess the fins are 6-inch diameter. I don't know what the diameter of this was, but a shiny surface, no fins. So the temperature rise was 65. That's probably 0.65 degrees C per watt. That's not 65 degrees C per watt. That's 0.65 degrees C per watt. 0.5. I don't know why the point's up there. Now, axial fins like that, this is all natural convection. So it drops to 45, but if you mount the fins the other way, it drops to 38. but if they're black, it drops to 34. Here, if they're vertical, it's 0.38. If you use the concentric fins but mount it vertical, it goes up. But if you paint it black, it goes back down again. So this is some very important data, and you can use these relative numbers and apply these percentages to any of your machines. It's very useful, real data. Oh, here's a case where you've got a black motor with fins. This machine here, and they blew 150 cubic feet a minute across this thing through a fan mounted on the end. And the degree C is 0.19 degrees C per watt. Significant difference over this guy to that guy, you know, or any of these. It's quite impressive. So it's always good to, I always recommend that you monitor the temperature of stators. If you use thermocouples, I prefer RTDs, but use thermocouples or RTDs and mount those inside the stator so that you can measure the temperature for R&D purposes, or measure the temperature to tie that in with control, inverter control, so you cut back on the current before you fry the windings. This is a very good practice with the modern inverters. Some standard inverters you buy have this input. And so the best place to mount the RTDs is put one in the core and one in the coil surface, or any tapes. Or these are not good practices. None of these things are good practices. The best place is to put one in the slot and one in the end turns. That's the best thing to do. Don't put any out here. There's no purpose putting out here. And try to stick it in a slot between two sides of two different phases, if it's if possible. And then the end turns are the hottest, so try to insert one in here in the end turn somehow. I showed you this machine before, but this is a large view that's worth studying again. This is a big machine with big, long thermal diffusion distances. So I mean, they've done a lot of different things to deal with the heat and the mechanical issues of this machine. You can study that and learn from that. This is that special fin design I promised to show you. This is the Tesla motor that's used in the Tesla hybrid vehicle. And they have a housing and a frame here, of course, but what they did, rather than cast or extrude fins in the OD, they found a manufacturer that could very cost effectively make this finned ribbon candy sort of structure. It's made out of real thin aluminum, and it's very rapidly made like that. You buy this and wrap it around there and put a rolled piece of aluminum around it, and you got a nice cooling jacket for this thing, because you have contact with the housing all here and all along the radiuses all the way around, plus all the surface area you generate. With a fan on the end, you blow air through here, and it's very effective in cooling. So that we're almost done here. This is a kind of cross-sectional view of a big machine that shows the passages through the stator. This is a superconducting rotor, by the way, and this one has to be kept frozen all the time. You see, you got to keep this at cryogenic temperatures. I showed you a picture of the conductors, but this is, I thought you might find this interesting to cooling fluid is probably liquid nitrogen, I believe is what they use. So that's how that works. I guess this is a different sort of a view. This is a induction motor rotor or a synchronous wound field rotor with passageways through the rotor and the stator, and so you've got a heat exchanger here where you're taking the heat out of the cooling media, and it's recirculated, pressurized to go in the air gap and in the ID passages in the rotor. Here's a shaft, and there's passageways there that it's directed down into there and here, and there's some vacuum pump out here that causes a circulation, goes through heat exchangers to cool the motor. These are how you cool great big machines, and I think some of these things have to be applicable to smaller machines. This is a small motor that has a kind of a clever centrifugal fan mounted here that it causes. See, where's the inlet? I'm looking. Oh, the inlet is through this screen here at the end, so it sends air through passageways in the stator yoke, like I described before, and out here it sends it through holes in the rotor, and it sends it through the air gap. And so, I mean, some scheme like that you could certainly incorporate into a motor design. These are some cooling zone description, rotor and stator cooling zones. These are zones. This is from a very large General Electric power plant generator. This is a typical plot that you would get. This happens to be a Infolytica 3D thermal model, finite element 3D finite element model for this is a traction motor for a vehicle, and it's a big one. It's 100 watts or 100 kilowatts, excuse me, and 100 kilowatt machine, and it has internal spray cooling on the rotor and the stator. Has a bunch of spray nozzles that have been modeled, and you see here that the temperature rise over time. This is the type of thing you want to study. That first of all, it's got to level out. It's got to terminate. Can't keep rising, or you don't have enough cooling. And it took this thing about 30, 40 minutes to get up to. Certainly, it stabilized after an hour. So for intermittent duty, you could work this motor a lot harder for 10 minutes or 5 minutes or something like that. I think that's clear from this. You could do these kind of models with some duty cycle and see it go up and down as during those temperatures of all these things will drop during the off times and then go back up. So you could study this temperature rise graphs, and each one of these color codes a different part of the motor. Now you see the housing is the coolest because that's the coolest part of the thing. The hottest are the probably the end windings, I believe. There's a left end winding and a right end winding, and you notice how when startup the thermal time constant of some of the components is different than the other. They actually cross over here. The stator left winding actually heated up first, and then as the cooling affected versus its mass, it actually cooled down a bit. And this blue, and what's the blue? And I guess it's the rotor bars. They didn't cool. That's what limits the temperature of this machine, are the rotor bars, not the stator conductor. So that's the type of analysis you have to do to really predict what the motor is going to do. Either use a lump parameter method to do this or a finite element method. So that concludes this last thermal article. Thank you.